Good day, everybody. In previous chapters, we have discussed how fast a reaction occurs. That's the chemical kinetics. We also discussed how far a reaction proceeds in the chemical equilibrium. We have also discussed the various factors that affect the reaction kinetics and the chemical equilibrium. In this chapter, we'll discuss why some reactions proceed spontaneously and go to completion, and some do not. The study of why reactions proceed or not is called thermodynamics and is related to the relative energy of reactants and products. In this section, we begin our discussion of reactions and the processes that proceed spontaneously, then end some of the factors that contribute to this phenomenon. Some chemical reactions, like combustion, are examples of spontaneous reaction. A spontaneous reaction or process is defined as one that once started, it occurs without continuous outside intervention. It can occur without continuous input of external energy. In contrast, a non-spontaneous process only occurs as long as energy is being supplied to the system. For example, the reverse of a combustion reaction, that is, the conversion of carbon dioxide and hydrogen and water to organic compounds, is not spontaneous, but does proceed during photosynthesis as long as energy in the form of sunlight is supplied. Also, spontaneous is not synonymous with fast. The conversion of iron to rust is not necessarily fast, but it will occur spontaneously, as we have observed during our daily life. Please also note, spontaneity is not synonymous with exothermic. Although many spontaneous reactions are exothermic, for example, combustion or oxidation of iron, there are many spontaneous reactions that are endothermic, or the enthalpy delta H is greater than 0. For example, the neutralization reaction between sodium carbonate and acetic acid is endothermic, but it does proceed spontaneously. Clearly, there are other factors besides heat energy or enthalpy that affect the spontaneity of the reaction. To understand the other factors that affect spontaneity, consider the dissolution of ammonium nitrate NH4NO3 in water. And this process is an endothermic process that occurs spontaneously and has a practical application in cold packs. Although the solution process is endothermic, the process occurs spontaneously because the particles in the final state or the aqueous state have more freedom of motion when dissolved than in the initial state, which is in the solid crystals. This factor is common to many endothermic spontaneous processes. The freedom of motion of the particles in the products or the final state are greater than that in the reactants or the initial state. Additional examples include the spontaneous melting of ice from solid to liquid, and the evaporation of molecules of water from liquid to vapor. The water molecules have more freedom of motion in the final state. The so-called freedom of movement can be understood in terms of molecular motion. In the solid state, water molecules may have vibrational motion, but have very limited motion in other directions. As they convert from the solid to the liquid state, molecules have more rotational motion, but still have limited translational motion. In the vapor state, there is a great increase in the translational motion because of the space between the molecules. The increase in the molecular motion can explain the spontaneity of melting and evaporation. These are physical changes. If we review the spontaneous reaction of sodium carbonate sodium bicarbonate reacting with acetic acid, we see that one of the product is CO2 gas. The gaseous molecules have much greater molecular motion, which contributes to the overall spontaneity of the reaction, even though it is endothermic. So far, we have learned that there are actually two factors controlling the spontaneity of a chemical or physical process. The first is the enthalpy of the process. The second is the entropy of the process. As molecules gain freedom of motion, their kinetic energy is spread out over more states of motion. This spreading out of energy is the key characteristic of spontaneous process, and entropy is defined as a measure of how energy is dispersed in the reaction or a physical process at a specific temperature. Energy is more dispersed, that means higher entropy, because entropy indicates the degree of the energy dispersal. We can predict whether or not a reaction is spontaneous using the second law of thermodynamics. The second law states that the entropy of the universe increases for a spontaneous process. Or we can say that delta S for the universe is greater than 0 for a spontaneous process. Similarly, if the delta S for the universe is smaller than 0, then the process is non-spontaneous. When delta S for universe is equal to 0, that means the reaction is at equilibrium. Please note, we have already learned that the universe is the sum of the system being considered, for example, the reaction or the physical process, plus the surroundings, which means everything else other than the reaction or the physical process. The change in the entropy of the universe is the sum of the change in the entropy of the system and the change in the entropy of the surroundings, as you can see in this equation. Consider the combustion of methane to produce carbon dioxide gas and the liquid water. That is, you have methane reacting with oxygen. It generates carbon dioxide and water. Water can be in gas phase or liquid phase, depending on the temperature. Here, let's say it's at a lower temperature. The entropy of the system must decrease because, in this case, because the reactants, which is the methane and oxygen, let's balance this equation actually. Because the reactants, which is the methane over here, and the oxygen gas, they have more freedom of motion than the products. We do have carbon dioxide still in the gas phase, but the water is in liquid phase, which means it has less freedom of movement in liquid water. However, the entropy of the universe increases because the entropy of the surroundings, in this case, increases dramatically upon the release of heat for the exothermic process, which increase the kinetic energy of the molecules in the surroundings. Or in another word, the surrounding will undergo the entropy increase in this case. For the system, the entropy will decrease. But the result is the overall change in the entropy for the universe is greater than 0. So this combustion process for methane reacting with oxygen is spontaneous. So how do we define the entropy? We can define the entropy change for an isothermal process, or so-called under constant temperature, okay, as indicated on this slide. The relationship between the entropy change and the heat depend on temperature. Adding heat increases kinetic energy, and the relative increase in the kinetic energy will be greater at the lower temperature. If T is smaller, the change of delta S will be greater. So the ReV in this subscript for heat refers to reversible process. So what is a reversible process? A reversible process is one that can be run in the forward and the reverse directions in such a way that there is no net change in energy flow in or out of the system. In other words, everything in this system goes back to its original state. That is the way it was before the process began. In reality, though, it's really rare to have anything that is completely reversible. However, theoretically, it could be very close. We could find reactions that are very close to a reversible process. To understand how the entropy change of the system and surroundings contribute to the entropy change of the universe, consider 1 mole of ice at 0 degrees C melting on the countertop at 22.0 degrees C, which requires 6.01 kilojoule of energy. Remember, at 22.0 degrees C, which is higher than the melting point, the melting of ice is a spontaneous process. When you calculate the delta S for the system, okay, for a reversible process, the delta S for the system is Q for the system divided by the current temperature in Kelvin scale. So you do this calculation and you find out the delta S for the system is 22.0 joule per K. And suppose the 1 mole of ice melts at room temperature on the countertop. The heat flows out of the countertop. So for the surrounding, the Q for the surrounding divided by temperature in Kelvin gives the delta S for the surrounding, which is calculated to be negative 20.4 joule per K. So the delta S for the universe, which is the total for the delta S for the system and that of the surrounding, is greater than 0. According to the second law of thermodynamics, the process is spontaneous, as we have already known before we started analysis, because we do know ice melts above 0 degrees C. So when you look at the example for ice melting we just discussed, the change in the delta S for the system, surroundings, and the universe are summarized for the melting of 1 mole of ice, which requires 6.01 kilojoule of energy. Because the entropy change of the system occurs at lower temperature, the change in entropy for the system is greater, resulting in a positive delta S universe and a spontaneous process. If the temperature of the surroundings was lower than the temperature of the system, or, for example, liquid water at 0 degrees C in the freezer at negative 10 degrees C, then the change in entropy for the system would be negative. Heat flows to the surroundings, and the entropy change of the surroundings would be positive. Because of the surroundings are at a lower temperature, so the delta S for the surrounding is greater than 0. Is greater in magnitude. So for this reason, the delta S is greater, delta S for the universe, which is the total for that of the delta S for the system and delta S for the surrounding. So the total is actually greater than 0. The whole process is a spontaneous process. So let's summarize the conditions that will produce a spontaneous process. If the entropy change for both the system and the surroundings are positive, both are positive, okay, then the process is always spontaneous. If both are negative, then the process will never be spontaneous. Okay. If one is positive and one is negative, then it will depend on which one is greater in magnitude. If the negative entropy change is one of greater magnitude, then the overall process will not be spontaneous. If the positive entropy term is of greater magnitude, then the process will be spontaneous. We have seen that entropy depends on temperature. As we lower the temperature, we decrease the kinetic energy of the molecules, therefore decrease the entropy of that substance. In principle, decreasing the temperature of a substance to absolute 0 or 0K causes all molecular motion to cease. If the substance crystallizes in a perfectly ordered crystal, then the entropy of the substance is equal to 0 joule per K. The principle of decreasing kinetic energy and the molecular motion with decreasing temperature leads logically to the third law of thermodynamics, which tells you the entropy of a perfect crystal is equal to 0 at absolute 0 or 0K. Setting a 0 point for the entropy scale allows us to establish absolute entropy values at other temperatures. We define the standard molar entropy as the absolute entropy of 1 mole of any substance in its standard state at 298 K or 298.15 K and the 1 bar of pressure. But remember, some textbooks still use 1 atm as the pressure. Absolute entropies are typically determined by careful measurement of molar heat capacities as function of temperature. So one more time, 1 bar is what's recommended, but many textbooks still use 1 atm as the pressure. The standard states of substances are listed in this table. For solids, liquids, and gases, it refers to the pure substance in its most stable allotropic form, if applicable. For substances dissolved in solution, it refers to a concentration of 1 molar. For practical purposes, 1 bar is essentially equal to 1 atm. That's why we still have some textbook listing 1 atm as the standard pressure, because 1 bar is very, very close to 1 atm. Remember, since 1982, 1 bar has been the standard pressure for tabulating all thermodynamic data. Before 1982, standard pressure was 1 atm. But if you use 1 atm, we would still consider that as correct, as I just explained. The standard molar entropies of various substances are provided in this table for comparison. The values for water in the liquid, vapor state illustrate what we have discussed previously. The entropy increase to 188, from the liquid state, which has lower entropy. A similar trend is seen when comparing liquid methanol, ethanol, butane, benzene to the entropy of the same substances. As you can see, gas phase has larger entropy than that of the liquid phase. Okay. Gas phase, large entropy. Liquid phase, small entropy. Because in gas phase, there is more space, there is more freedom of movement. When you compare the entropy for diamond and graphite, graphite has about twice as much as that of the diamond. It's because of the structural feature of diamond, which is a network type of structure, and the graphite is a layer type of structure, which offers less rigidity in the structure. So usually, as you can see, for the same substance, the entropy for the gas will be greater than the entropy for the liquid, and it will be greater than the entropy for the solid phase. These trends in the entropy with phase changes are illustrated in this figure. Note the general trend in the increased entropy as temperature increases for a substance. We emphasize it's in the given phase. Also, note the significant, look at here, so when you increase the temperature, okay, in the same phase, the entropy does increase. But when you have phase change, you see a jump in the magnitude of the entropy. For example, from solid to liquid, it jumps a little bit. But you see a bigger jump from liquid to gas phase. But in each phase, you still see the same trend hold. Because when you have a higher temperature, you have higher kinetic energy, you will have bigger entropy. Also note that the lines are not straight. The increase in entropy with temperature becomes smaller as temperature increases. We can calculate the delta S for vaporization as the difference between the molar entropies of liquid water and the gaseous water at the boiling point. We can summarize the factors that contribute to energy changes discussed so far. Entropy increases as temperature increases due to the increased kinetic energy. Entropy increases as volume increases because of the more available molecular motions. So these two factors, temperature and volume, we have discussed this very thoroughly. Entropy increases as the number of independent particles increase. That's another layer of factor. Because the energy can be distributed over more particles. So if the molecule is more complex, you will see more ways to distribute the total energy. Thus the entropy will increase. Entropy increase with the molecular complexity, as you can see in this example listed over here. As the molecules become more and more complex, the entropy increases as well. So temperature, volume, and the molecular complexity. Molecular complexity affects the entropy. In general, standard molar entropy increases as the complexity of the molecular structure increases. For example, we have C2H4, and we also have carbon monoxide. Okay. The entropy for these two molecules, which both has about 28 grams per mole, so the size, molecular size is about the same. Both has about 28 grams per mole. Okay. However, because C2H4 is more complex than the structure of CO, so the entropy of ethylene is actually greater than that of carbon monoxide. This concept is illustrated for the series of alkanes shown here: methane, ethane, propane, and butane. As more atoms are added to the chain, the entropy increases, the molar mass increases. Another factor is the molecular rigidity, as we talked about in previous slide for the examples of a diamond and that of graphite. As we mentioned, carbon in the rigid diamond structure has less entropy than the carbon in the less rigid graphite form. Similar to enthalpy and internal energy, entropy is actually a state function. So we can calculate the change in entropy as the difference between the entropy of the initial and the final states. So we can calculate the delta S for the reaction by totaling up the entropy for the reactants, for the products minus that for the reactants. The N indicates the chemical coefficients of the products and the reactants. If you recall, we have learned previously in General Chemistry 1 that delta H for the reaction is the total enthalpy change for the products minus the total enthalpy change for the reactants. Okay. So similarly, for the Gibbs free energy change, which we will talk about in a little bit, because it's a state function, so you can also do the calculation similarly. So we have three very similar equations for entropy change, for enthalpy change, and the Gibbs free energy change for the chemical reaction. So the entropy change for the system, as we just discussed, can be calculated using this equation, and the entropy change for the universe can be calculated in another equation which we have already discussed, which is for a reversible process, the delta S for the surrounding equals the heat over time. Do remember, under constant pressure, Q for the surrounding is the negative delta H for the system. Okay, so in other words, you can rewrite this entropy change for the surrounding as negative delta H for the system over time. So over temperature. Okay, excuse me. and this would be constant, and the constant pressure and the constant temperature. Let's work on a practice question. So in this question, we're asked to use the values from the appendix table. Okay, calculate the standard entropy change for the reaction. In this reaction, we have some reactants and some products. Remember, so we can calculate the change of entropy by adding up the total entropy change for the products and do the entropy change for the reactants and do the difference of the two. So we can substitute the numbers in. You can look up these numbers in the appendix table. In your exam, these numbers will be provided. Okay, so you do the difference between that for the total for the products. So if you really want to write this thing, it should more correctly, it should be sigma n times S for the product, okay, minus the total for the S, N for the reactants, and for the S for the reactants. You do the calculation and you find out that delta S for the reaction is a negative number. The result does make sense because in the beginning we have 2 plus 7 moles of gas. After the reaction we have 4 moles of gas. Remember, in this case, water in this case is in liquid phase, so we have less moles of gas being generated, so we expect the reaction to have a decrease in entropy. Previously, in one of the slides, we talked about Gibbs free energy. So what is Gibbs free energy? We define the Gibbs free energy of a system as the maximum energy released by a process at constant temperature and pressure that is available to do work. We previously predicted the spontaneity from entropy of the for the entropy of the universe. Okay, for a spontaneous process, this is greater than 0, and because we know delta S for the surrounding, remember, equals negative delta H, okay, for the system divided by T. Alright, so you substitute this equation in, right, and rearrange it. You will see on the left side you only have universe as what you study, and over here on the right side everything's converted to some quantity related to the system. So for this reason we define this delta G to be negative T times delta S for the universe. Okay, then everything will be related to the system, but you don't have to write the system as the subscript. Okay, if you don't write the subscript, we simply assume everything is related to the system. So by this definition, we are able to relate the delta G to two factors, which is delta H and delta S, the enthalpy change and entropy change. So Gibbs free energy equation, delta G, is equal to delta H minus T times delta S. We can summarize the process that contributes to a spontaneous process from our previous discussions. The spontaneity, remember, is favored by increase of entropy of the system. The spontaneity is also favored by exothermic processes. So under these two conditions, the spontaneity is favored. Either you have an increase of entropy or you have an exothermic process, or delta H is smaller than 0. The free energy relates both enthalpy and entropy. The advantage of this equation is that all parameters are related to the system. Enthalpy and entropy are also state functions, so delta S and delta H can be calculated knowing the appropriate values for the reactants and the products. Conveniently, standard free energies of formation are also state functions. We define the standard free energy of formation, delta GF, as the free energy change associated with the formation of 1 mole. It's 1 mole of its standard state form of the element. Okay. So when you do the calculation for delta G for the reaction, as we previously discussed, it's very similar to the delta H for the reaction calculation and that of the delta S for the reaction. Okay. So I'm not going to write down all the details because we just talked about it. And remember, the N over here is the chemical coefficients of the products or reactants in the balanced chemical equation. Let's work on a problem. Use values from Appendix 4, calculate the free energy changes for the following reaction. Remember, these are given from the table. So when you do the calculation, you simply do the total for, so I'm going to rewrite it, the total, N for NP, that means for the product, okay, delta GF for the products minus total for the reactants, N subscript R means it's for reactants, and the delta GF for the reactants. So you substitute the numbers in. This is the product. So it's 2 times that of CO2, 2 times that of CO2, plus 3 times that of the water. Remember, water exists in different phases. When you look it up in the table, do make sure you have the right phase matched. Over here it's liquid phase, so use the liquid phase value. Okay, and then minus the total for 1 mole of methanol and 3 mole of oxygen over here. So you do the calculation, you find out that delta G is a negative number. And this does make sense because this process is a combustion process, and indeed it is a spontaneous process. For a spontaneous process, the delta G is smaller than 0. Summarize some of the things we just talked about the spontaneity. Okay, so we have learned through the second law of thermodynamics, if delta S for the universe, okay, if this is greater than 0, we know the process is spontaneous. Okay, if it's smaller than 0, it's non-spontaneous. And if it's equal to 0, that means the reversible, this process is reversible, or we can say this process is at equilibrium. Or we can call this reversible. So similarly, do remember, because delta G is defined as negative T times delta S for the universe. So if delta S is greater than 0, delta G will be smaller than 0. So for delta G for the system, or simply delta G, for a spontaneous process, it will be smaller than 0. Non-spontaneous, delta G will be greater than 0. And if the system is at equilibrium, the delta G will be equal to 0. And this process is at equilibrium when delta G is equal to 0. So, what is this Gibbs free energy? What really does it mean? We have the definition. We know delta G is delta H minus T times delta S. And we also previously defined the free energy as the energy available to do useful work. So what is useful work? We can define the useful work by way of an example, the combustion engine. The internal energy was defined previously by delta E is Q plus W. For the combustion reaction in an engine, the exothermic reaction means heat is lost from the system, or Q is negative. So internal energy decreases. As the pistons move due to the expansion of gases, work is done by the system on the surroundings. So W is also a negative sign because system is done on the surrounding. The amount of work that can be done is W equals P times delta V. It's a negative P times delta V of the heat released by the reaction, or the delta H. Okay, some can be used to do work, which is defined as delta G, and some is redistributed in the molecular motion of the products in the form of entropy, delta S. So in reality, not all the energy associated with delta G actually goes toward the usable work, because the reaction takes place under irreversible conditions and some heat is lost to the surroundings. So we can define the efficiency of the process as the work actually performed relative to the amount of energy produced by the combustion reaction. Not all energy can be useful. Some of them are wasted in the form of heat. And the portion that can be used to do useful work is defined as the Gibbs free energy. We have already learned for a spontaneous process, delta G is smaller than 0. Okay? And for a non-spontaneous process, delta G is greater than 0. Since delta G equals delta H minus T times delta S. So we must examine both the enthalpy and entropy changes associated with the process at a given temperature to determine the spontaneity. Please note, when delta H is smaller than 0, or if it's negative, okay, the spontaneity is favored. Okay, hope you still remember that. And for delta S, if entropy is increasing, right, the spontaneity for the process is favorable, or it's favored. Okay, so these are the two factors we've been emphasizing all along. So if both factors are favorable, for example, delta H is smaller than 0 and delta S is greater than 0, so your delta G will always be smaller than 0. In this case, no matter what temperature this is, it will always be spontaneous. Right? If both are disfavored or it's unfavorable, for example, delta H is greater than 0, that's unfavorable. Delta S is smaller than 0, it's unfavorable. So delta G will always be greater than 0 in this case. It will never be spontaneous at any temperature. However, if one is favored and one is disfavored, for example, delta H is smaller than 0, that means it's favored in terms of delta H. However, delta S is disfavored. In this case, the process will be spontaneous only at low temperature. Okay, so if it's negative, it will be spontaneous at low temperature. If it's positive means delta H over here is disfavored. However, for delta S, that's favored in this case. So if both are positive, it will be spontaneous only at relatively higher temperature. But do remember, so-called lower or higher, it's a relative number. It's not an absolute number. For example, for one process, 1000 degree, it might be a low temperature. But for another process, 0 degree, it might be a high temperature. So that's what I meant about higher or lower temperature. For more examples or practice, please look at the practice questions in the problem set. We have seen previously that we can use free energies of formation and the fact that delta G is the state function to calculate the delta G for the reaction using this equation. But how do we calculate the delta G under non-standard condition? Delta G under non-standard condition is related to both the delta G naught, which is the Gibbs free energy under standard condition, and the actual R times T and times the natural log of reaction quotient. Remember, if the reaction is at equilibrium, then that means the delta G at this point is 0. So if this is 0, you can actually calculate, because this Q would be the same as K at equilibrium. So you substitute this in, you will have delta G naught, okay, relationship with reaction equilibrium constant. So as you can see, when temperature change, K does change with it. Clearly, we can calculate the standard Gibbs free energy change using the equilibrium constant. Similarly, if you want to calculate the equilibrium constant given the Gibbs free energy, you can use this equation. For more practice questions, please refer to the problem set. The relationship between delta G and equilibria is illustrated in this figure for the reaction of N2O4 in the equilibrium with 2NO2. Using the standard free energies of formation, we can calculate the delta G of formation for the products and the delta G formation for the reactants for the overall delta G. And we can find out for this reaction that delta G for this reaction, okay, is actually 4.8 kilojoule. And we just simply done this by using delta G for the reaction equals sigma n for the product and delta G formation for the products minus that for the reactants. And remember, the delta GF values will be given in your exams, but you can always find this in the appendix table. Let's talk a little bit about the relationship between delta G naught and the K. All right. So apparently, delta G naught equals negative RT times natural log of K. So if delta G naught is smaller than 0, we do know that means K is actually greater than 1. The reaction will be spontaneous. If delta G naught is greater than 0, it's the same as saying K is smaller than 1. But do remember k is a positive number, so it's always greater than 0. It's not going to be smaller than 0. Okay, and this process will be non-spontaneous. Okay, if delta G is 0, then this is the same as saying k is equal to 1 and the reaction is at equilibrium. So in the picture you see over here, the equilibrium constant is much, much greater than 1. That means the reaction almost goes to completion. That means delta G naught will be a very negative number. If k is just a little bit greater than 1, delta G is just a slightly negative, and the k will slightly favor the product. Okay. So if k is smaller than 1, but do remember k is always greater than 0. K is always greater than 0. Okay. So what do you mean? Much greater, much smaller than 1. That means, for example, k equals 10 raised to negative 10th. You see, that's a very small number. That means delta G will be greater than 0. Okay, and it will be a very positive number. Let's do a practice question. Using delta GF values from the appendix 4, calculate the value of delta G naught for this equilibrium and calculate the equilibrium constant for this particular reaction. First, do remember we can find the delta G values in that table and calculate delta G for the reaction using this equation. Okay. Then substitute the numbers in delta G naught equals negative RT times natural log of k. You will be able to calculate the k because we do know k would be E raised to delta G naught over RT. So let's work on the details. Substitute the numbers into this equation, then you find out your delta G. Okay, is negative 41 kilojoule per mole. But do remember, when you substitute into this equation to find the k, do remember you got to convert 41.06 kilojoule to joule. So you multiply by 1,000. Okay, so it's kilojoule per mole per k over here. So k is cancelled out. Then your the Kelvin is cancelled out. Then you have the equilibrium constant value as a very big number. So k over here is much greater than 1, which means this process is spontaneous. This does make sense because we have already calculated the k to be a very negative number. Okay, we calculated delta G to be a very negative number. When delta G is smaller than 0, that's the same as saying k is greater than 1. When delta G is very negative, that means k is much, much greater than 1. So, as it turns out, this k is a large number, which does make sense. So when we were talking about the chemical equilibrium, and we mentioned the equilibrium constant is dependent on temperature, let's talk about the details. As derived previously, we have a relationship between delta G, delta H, and delta S. We also have a relationship between K and delta G. So by combining these two relationships, we will have natural log of K is equal to this. If you plot natural log of K against the inverse of T in Kelvin, okay, you would get the slope. So let's say this is the Y, and that's the slope. That's the slope, okay. So negative delta H over R. So this Y is natural log of K, and X is inverse of T. So basically, you plot natural log of equilibrium constant against the inverse of T. You will have a slope that is negative delta H over R, and intercept is delta S over R. This concept is illustrated in this figure for the reaction of carbon dioxide to form carbon monoxide and oxygen. So this is the actual reaction. Okay. Based on experimental data, we have this plot over here, and you will be able to plot the natural log of equilibrium constant versus the inverse of T. Let's do a practice question. At 2000 degrees C, the value of Kc of the reaction is given. And what is the value at different temperature? Okay, so we can use the two-point equation to do this calculation, because one is not given. This is given. Temperature is given. Temperature is given. Delta H is given. So we can substitute the numbers in and do the calculation. As you can see, we can substitute the numbers in and do the calculation and find out what the equilibrium constant is at a different temperature. And this turns out to be a much smaller number. In living systems, spontaneous reactions typically involve the metabolizing food to provide energy needed by the body, while the reactions that are involved in building molecules, such as proteins and so forth, are non-spontaneous. The living systems use the energy from spontaneous reaction to run non-spontaneous reactions that are essential to life. This is accomplished by coupling, also called combining, a non-spontaneous process to a spontaneous process, and then the total process is made spontaneous. And these processes are covered in greater detail in chapter 20. Okay. So the basic principle is you combine a spontaneous process with a non-spontaneous process, and the combined process is made spontaneous. In previous section, we introduced the different types of molecular motion and how they were related to the freedom of movement in a given physical state. And we mentioned translational motion and rotational and vibrational motion. Okay. The translational motion is related to the movement of a molecule through space. Rotational motion is related to how a molecule spins around its axis or a point. Vibrational motion is related to the movement of atoms in a covalent bond toward or away from each other. Like this is away from each other, toward each other. As temperature increases, all of these types of molecular motion increase. As mentioned in our discussion of quantum mechanics, energy in the molecules is quantized. In other words, there are discrete energy levels related to different types of molecular motion. We define the so-called microstate, okay, as a unique distribution of a particle across the possible allowed energy levels in the system. The concept of energy level is illustrated in this figure. Right. In the vibrational system, okay, You also have vibrational states, which is quantized, as you can see over here. How to link the microstates to entropy, and this is defined by the Boltzmann equation. Entropy is defined as Boltzmann's constant times natural log of the number of microstates, and the entropy increases as the number of microstates increases. The statistical view of entropy is compatible with the other macroscopic views discussed previously. For example, increasing the number of molecules in the gas phase increases the number of transitional states available. Increasing molecular complexity increases the number of vibrational states within each molecule. Increasing the temperature will increase the number of energy states associated with all types of molecular motion. It's also consistent with the third law of thermodynamics. For a pure solid in a perfectly aligned crystal, there is only one possible distribution of the particles in the system. Since there are no states associated with the molecular motion, from the Boltzmann equation, the result is the entropy S will be 0, because under that perfect crystal at 0 degree K, the W is 1, natural log of W will be 0, or entropy S will be 0. So hopefully through these examples we are able to relate what we have already learned to this statistical view of entropy defined by Boltzmann equation over here. So that's it for today. Thank you very much, and for more practices, please look at the problem set, and see you next time. Bye.